Okay, so we are starting chapter 7. It's one of my favorite chapters. We're talking about statistics, and I wanted to show you a short video that kind of puts in perspective why it's important for you to be able to wrap your head around what statistics mean and making decisions in just everyday life and how they apply and how easy it is for somebody to use statistics in a way that may confuse people and almost have them believing something that is not true. So I'm going to start off by showing you this short video.
Statistics are persuasive, so much so that people, organizations, and whole countries base some of their most important decisions on organized data. But there's a problem with that. Any set of statistics might have something lurking inside it, something that can turn results completely upside down. For example, imagine you need to choose between two hospitals for an elderly relative's surgery. Out of each hospital's last 1,000 patients, 900 survived at Hospital A, while only 800 survived at Hospital B. So it looks like Hospital A is the better choice. But before you make your decision, remember that not all patients arrive at the hospital with the same level of health. And if we divide each hospital's last 1,000 patients into those who arrived in good health and those who arrived in poor health, the picture starts to look very different. Hospital A had only 100 patients who arrived in poor health, of which 30 survived. But Hospital B had 400, and they were able to save 210. So Hospital B is the better choice for patients who arrive at hospital in poor health, with a survival rate of 52.5%. And what if your relative's health is good when she arrives at the hospital? Strangely enough, Hospital B is still the better choice, with a survival rate of over 98%. So how can Hospital A have a better overall survival rate if Hospital B has better survival rates for patients in each of the two groups? What we've stumbled upon is a case of Simpson's paradox, where the same set of data can appear to show opposite trends depending on how it's grouped. This often occurs when aggregated data hides a conditional variable, sometimes known as a lurking variable, which is a hidden additional factor that significantly influences results. Here, the hidden factor is the relative proportion of patients who arrive in good or poor health. Simpson's paradox isn't just a hypothetical scenario. It pops up from time to time in the real world, sometimes in important contexts. One study in the UK appeared to show that smokers had a higher survival rate than non-smokers over a 20-year time period. That is, until dividing the participants by age group showed that the non-smokers were significantly older on average, and thus more likely to die during the trial period, precisely because they were living longer in general. Here, the age groups are the lurking variable, and are vital to correctly interpret the data. In another example, an analysis of Florida's death penalty cases seemed to reveal no racial disparity in sentencing between black and white defendants convicted of murder. But dividing the cases by the race of the victim told a different story. In either situation, black defendants were more likely to be sentenced to death. The slightly higher overall sentencing rate for white defendants was due to the fact that cases with white victims were more likely to elicit a death sentence than cases where the victim was black, and most murders occurred between people of the same race. So how do we avoid falling for the paradox? Unfortunately, there is no one-size-fits-all answer. Data can be grouped and divided in any number of ways, and overall numbers may sometimes give a more accurate picture than data divided into misleading or arbitrary categories. All we can do is carefully study the actual situations the statistics describe, and consider whether lurking variables may be present. Otherwise, we leave ourselves vulnerable to those who would use data to manipulate others and promote their own agendas.
Now, we kind of talked about some of the things in that video covered back in chapter 3 when we talked about combining things that made statistics maybe a little bit misleading or have a different meaning than they really do. So we're going to kind of delve forward and talk about how do we really wrap our mind around what these statistics really mean? How do I know when somebody says that you have a 25% chance of this happening to you? How do I know that that's real? So we're really going to delve into understanding how we come up with these calculations. So this first problem says, suppose there are 25 students in your math class. What is the probability at least 2 students in the class have the same birthday, such as February 5th or July 2nd? Okay, I just want you to kind of ponder over that and think about it. I don't know if we're going to answer it right now. I do want you to kind of think, well, we've got some options here about 0.01, which would be 1 in 100. We have 0.25, which is 1 out of 4. And remember that, just to go back, that to get a decimal to a percent, you would need to multiply by 100. So this is really 1%. This would be 0.25 times 100, which is approximately 25%. Okay, 0.6 times 100, which is 60%. Okay, and these, to get a fraction into a percentage that you can talk about, you would need to do 2 divided by 365 and then multiply by 100. 25 divided by 365 times 100. And when we do these calculations, this one comes up to be about 0.54%, which is really small. And then this one comes up to be about 6.8%. Okay, so it seems kind of crazy to think that if there's 365 days in a year, right? So if you've got somebody in that class that has the exact same birthday as you, seems like that would be a very small percentage, because we've got such a big number of birthdays that we could be. There's 365 days in a year. So I'm going to come back to this question probably at the end of this class, and I also want to look at it at the beginning of next class. But just kind of think which option you think might be correct, okay? So when we consider tossing 2 coins consisting of a head and a tail each, what are the possible outcomes? So how many heads were in each outcome? Well, I mean, we only have 2 choices. If we can toss coin 1 and we can get a heads on coin 1, and we could get a heads on coin 2. Or we could toss coin 1 and get a heads, and coin 2 could be a tails. Or we could toss coin 1 and it be tails, and coin 2 could still be tails. Or coin 1 could be tails and coin 2 would be heads. But this picture is basically everything that I could come up with. Okay, so it says how many heads were in each outcome, which is what this is asking. So this one had 2 heads, right? This one had 1 head, 1 tail. This one had 0 heads, and this one has 1 head. Okay, so, and we could come down here and we can go ahead and write 1 tail, 2 tails, and 1 tail. It says outcomes are the most basic possible results of observations or experiments. For example, if you toss 2 coins, one possible outcome is a head and a tails, which is the one we got right here. Another possible outcome is tails and heads, which is the last one that we got. So an event consists of one or more outcomes that share a property of interest. For example, if you toss 2 coins and count the number of heads, the outcomes, heads, tails, and tails, heads, both represent the same event of 1 head and 1 tail. Okay, so what they're saying is that this is 1 head and 1 tail, and this is also one head and one tail, well, those are the same outcomes. They're just flipped among the coins. Okay. So consider families with 2 children. List all the possible outcomes for the birth order of boys and girls. If we are only interested in the number of boys in the family, what are the possible events? So we'll use B to represent a boy and G to represent a girl. So there are going to be 4 possible birth order outcomes. Okay, we could get 2 boys. Okay, we could get a boy and a girl. We could get a girl and a boy. And we could get 2 girls. Because we are asked to consider only the total number of boys, the possible events with 2 children are, well, we could have 0 boys. So this right here represents the fact that we would have 0 boys. That would be an event. Okay, we could have 1 boy. So this represents something else, and this has 1 boy, and so does this one. Or we could have 2 boys. The event 0 boys consists of the single outcome, which is this one, right? This is a single outcome. The event 1 boy and 2 boys. The event 1 boy consists of the outcomes of these 2. So this is another outcome that we could have, 1 boy, and the event 2 boys consist of this outcome. So there ends up really being just 3 outcomes. These are my 3 possibilities. I could have 2 boys, I could have 1 boy, or I could have 0 boys. Okay. The probability of an event expressed as P of an event is always between 0 and 1. So what does that mean? Okay. So if the probability of the event is 0, it didn't happen. It's impossible. When we get closer to moving up to 0.5, maybe let's say 0.1, well, 0.1 would be 10%, and then the probability is pretty unlikely. Okay, we could jump up to 50%, and the probability becomes a little bit more likely. And then if we get up to closer to 1, like 0.75, that would be 75%. We're getting a lot more likely that it's going to happen. And when we're at 1, that's 100%. That means it's going to happen. Okay? So what is theoretical? What's the theoretical method? The theoretical method for equally likely outcomes. The first thing you want to do is you want to count the total number of possible outcomes. Among all the possible outcomes, you count the number of ways the event of interest can occur. And then you determine the probability. So we've got the formula down here for the probability of A, that this event's going to happen, the number of ways it can occur over the total number of outcomes. Okay, so when we think about tossing a coin, I do want to bring this up here. When we think about tossing a coin, we know that most of us would be pretty content to say that we've got a 50% chance we're going to have heads and a 50% chance we're going to have tails. Okay, so that would be our theoretical probability, because we're 50% sure that just thinking about it, since it's one side is a head and the other side is tails, got a 50-50 chance. Okay, if we actually did an experiment with coins, we might find out that when we actually flip a coin 50 times, we don't get 25 heads and 25 tails, okay, because it's the actual experiment, and that's an experimental probability. But what you'll find is that your experimental probability will come closer to what you think should happen, or your theoretical probability, the more times you do the experiment. So I'm going to go to the graphing calculator real quick, and I'm going to show you, I'm going to ask you to pull out your graphing calculator and do this as well. But I want us to play with this for just a minute and see that your experimental probability will approach what your theoretical probability is the more times you do the experiment. Okay, so when you're looking at your graphing calculator, I'm going to ask everybody to kind of get out their graphing calculator and let's look at this. So what we kind of think happens is that if we're going to flip a coin, we should get heads 50% of the time and we should get tails 50% of the time. So if we actually do the experiment, which we're going to do with this calculator, I want you to go to your apps button, which is diagonal from the alpha. We're going to hit apps, and we're going to go, for most of you, you'll be able to find this program or this app on number 10. If you scroll past 9, it'll say probability simulator, and that's the one that we want to pick. Okay, so if we want to toss coins, which is what we're going to do, that's the activity we want, then you'll look at OK. Right underneath OK is your Y equals button, which is what you want to push. And we do want to toss the coins. And so I'm going to hit underneath toss. It says Windows. I'm going to go ahead and toss a coin. Well, here I go with my experiment. Obviously, on this one, I got one head, no tails. Okay, and if you look underneath here, we can kind of use these buttons down here to toss a bunch of coins at the same time. So I'm going to go ahead and say, I'm going to hit zoom and add 10 more. Whoa. Okay, so that's definitely not what I thought would happen. I thought that the tails and heads would start getting closer together, but I've only tossed this coin 11 times. So it is possible that I would get heads a lot more times than I would get tails if I only tossed it 11 times. So now I'm going to kind of jump up and hit this plus 50. I'm going to add 50 more experiments on top of this. So I'm going to hit the trace button. And I'm at 61 now. That's quite a bit more. And now it looks like heads is winning and tails is losing. Okay, but the bars are kind of evening out now. Let's add another 50. Okay, now we're at 111. And you can tell that we're really close to being the same. Let's keep going for a little bit. Let's add another 50. Okay, 161, we're pretty close. So your calculator should be doing similar to this. I'm going to go ahead and hit trace again. Now, there are going to be times whenever you start to see a difference again, like it looks like tails is winning by a little bit of a margin here. We've done this 211 times of flipping the coin. So I'm going to hit it again. There's 261, 311. Heads is starting to catch back up again at 361. At 411, we're getting very close again. So the more times you do the experiment, the closer you are going to get to what you think is going to happen, that it's going to be a 50-50 chance. But while we got our graphing calculator out, let's play with this for a little bit more. Let's go back to, let's quit this. So I'm going to hit escape, and so I'm going to hit Y equals. And I'm going to hit escape again, and it says, are you sure you want to get out of this? Yes, I do. And now I'm going to go down to the roll dice one. And we know that a die has 6 sides to it. So I'm going to try this one. I'm going to hit OK, so Y equals. And if I roll, what I think is going to happen, right, is I should get each one of these 1/6 of the time because there's 6 sides. So if I just roll the dice one time, so I'm going to hit window and roll the dice. Well, I rolled a 1. Okay, I'm going to roll it one more time. Rolled a 6. I'm going to hit window again, roll it again. Then we got a 4, 5, a 2, a 3. Now that was perfect, okay? That's not always what's going to happen. I'm going to hit escape. Let's clear this out. Okay, so I'm going to roll our dice. We got a 6 this time and a 5. Oh, wait a minute. This time I rolled 2 1s before I ever rolled a 2 and a 4. Okay, so that's kind of what now I've rolled another 5. And 2 and 4 didn't get rolled at all. But the more times I roll these dice, the more these columns should even out. So if I add 50 to those rolls, okay, it looks like one is still really winning. I added 50 more and I got 106. Still one's pretty far ahead. 156. Still I've got some discrepancy here. Going to keep going. 206 is making them a little bit closer together. 5 is still pretty behind. So I'm going to keep on pushing that until I've got, now 6 is way ahead, right at 306. But you'll notice that at 356, these are starting to kind of even out. They're starting to become more and more like what I think would happen. Okay, 456. So I've not got one that's way winning more than the others. So when you're doing an experiment, you want to consider the fact that you've got your experimental probability is going to get closer to what you think is going to happen, which is your theoretical probability, the more times you do the experiment. Okay, so on example 2, what do we think is going to happen here? If we have exactly one head when you toss 2 coins. Well, we've got all of our choices listed here, right? We could have 0 heads, we could have 1 head, and 2 heads. So it says exactly 1 head when you toss 2 coins. Well, it looks like that happens 2 out of the 4 times that we did the experiment. 2 out of 4, which is 1/2. Okay. If you're getting a 3 when you roll a die, well, if I rolled a die, I could get a 1, a 2, a 3, a 4, a 5, or a 6. These are all the possible choices. So out of those 6 choices, there's 1 out of 6 chance that I could get a 3. That would be the probability. And now the way we want to write this is we want to say the probability that we are going to get a 1 heads. Okay, well that's 1/2, 2 out of 4. So the probability that we're going to roll a 3 is 1 out of 6. Okay, let's just go back and look at the formula, make sure we're okay. Remember that we're doing the number of ways A can occur out of the total number of outcomes. So when we looked at these, we had 1 head here and 1 head here, which got us our 2, and then there were 4 outcomes, so that's why we were dividing by 4. We have 6 possible things that could happen, so that's why we've got 6 on the bottom, and one of them gave us the 3. That's why we have 1 on the top. So let's talk about playing cards. There are 52 cards in a standard deck. There are 4 suites known as hearts, spades, and diamonds, and clubs. Each suit has cards for the numbers 2 through 10, plus a jack, a queen, a king, and an ace, for a total of 13 cards in each suit. Notice that hearts and diamonds are red, while spades and clubs are black. If you draw 1 card at random from a standard deck, what is the probability that it is a spade? Okay, so we know that there are listed in each one of these, there are 13 cards in this one, 13 in this one, 13 in this one, and 13 in this one. And there are a total of 52 cards. So if we listed all the cards out separate, there are 52 cards. Okay, I have a chance that I could draw any of those 52 cards. They're all in the deck, so my possibilities would be 52. And there are 13 of them that are spades. So I have a chance, 13 out of 52, that I'm going to draw a spade. So what's the probability that we're going to draw a spade? It's going to be 13 out of 52. Now you want to see if this fraction will reduce, and we know that 13 times 4 is 52. So you could reduce this in your calculator if you want to, or you could use the fact that you know 13 goes into both of these. 13 divided by 13 is 1. 52 divided by 13 is 4. And remember, if we want to talk about the percentage, we would divide those and say 1 divided by 4 is 0.25 times 100 would give you your 25%, which makes sense. I mean, I've got 4 stacks of cards, so it would be roughly 1 out of 4 that I'm going to draw a spade. Now, if we actually did this experiment, we might find, like I was showing you on the graphing calculator, you might find out that it's not exactly what we thought was going to happen. The more times I do it, the more times I'm going to come closer and closer to getting that 25%. Okay, so there's something called the multiplication principle, and it says suppose there are m possible outcomes for one process and n possible outcomes for a second process. The total number of possible outcomes for the two processes combined is m times n. And so it says, what is the probability that a random selected family with 3 children has 2 girls and 1 boy? So we're going to use this to kind of talk about this multiplication principle. Step 1, you really need to find out how many possible outcomes we have. So how many possible outcomes are there? Okay, there are people who do this all different kinds of ways. I like to do a tree diagram to list them. I think it helps me organize my thoughts. So on child number 1, okay, child number 1 can either be a girl or a boy. And child number 2, so given that I had a girl first, on child number 2, I could still have a girl or a boy. If I have a boy first on child number 2, I could still have a girl or a boy second. Okay, on number 3, child number 3, I could have a girl or a boy. So on this one, this outcome would be this would be a girl, girl, girl. So now I can already see one of my possible outcomes. I could have all girls. Okay, or I could have a girl and then have another girl and then have a boy. So this one would be girl, girl, boy. This also helps me to not list things twice that so I get confused. So it helps me kind of organize my thoughts whenever I'm doing these tree diagrams. Then I could come down here and say, what about the boy? So if I went this way, this could be a girl or a boy. So if we follow this tree, it's going to be girl, boy, girl. And then the bottom half of that tree would be girl, boy, boy. Okay. Now, I'm going to keep going. Let's see what happens if we've got a boy, girl. Well, it could still be a girl or it could be a boy for the third child. If I follow this chain, we're going to get boy, girl, girl, and we're going to get boy, girl, boy. And then on this one, we've got a boy, and then we've got a girl and a boy. So we could have a boy, boy, girl, or a boy, boy, boy. This is trouble right here, right? Just joking. So those are my possible outcomes. So it looks like we have 1, 2, 3, 4, 5, 6, 7, 8. If I were to try to just list these without doing this tree diagram, I would get lost. Some of you may be able to do that perfectly without having to do that, and that's fine too. So I'm just trying to, this is a way to help you organize your data. So step number 2, of these 8 possible outcomes, 3 have 2 girls and 1 boy. So we need to find what we're looking for in the problem. We wanted to know which one has 2 girls and 1 boy. Okay, so when I kind of get this down, so I'm looking for over here and I'm saying, okay, all the first set of girls, and I want, so this one right here has 2 girls and a boy. This one has 2 girls and a boy. This one has 2 girls and a boy, but all the rest of these do not have 2 girls. So there's 3. The ones that we came up with is we could have girl, girl, boy. We could have girl, boy, boy, and we could have boy, girl, girl. Step number 3. The probability that a family with 3 children has 2 girls and 1 boy. Well, this is the way you would want to write that. The probability that we've got 2 girls and 1 boy, okay, is going to be equal to the number of outcomes with 2 girls and 1 boy, so the 3 of them, out of our total number of outcomes, which is 8. If we take that and we do 3 divided by 8, we get 0.375. If we multiply that by 100, we would get our percentage of 37.5%. Okay, so there's a 37.5% that if we have 3 children, order doesn't matter, that we would have 2 girls and 1 boy, it's 37.5%, which is actually what I have. I have a girl and then a boy and then a girl. So kind of neat. So this is going to be the last example we're going to look at in this class, and then we're going to come back and look at that first question that we kind of left off with. But it says, you select a person at random from a large group of attending a conference. What is the probability that the person has a birthday in July? Assume that there are 365 days in a year and births are equally likely to occur on any day of the year. So remember that each possible birthday represents an outcome. So we want to know how many possible outcomes we have. Well, that's going to be step 1. Well, there's 365 because there's 365 days in a year. And July has 31 days, so there's 31 events that are going to give us out of our 365 outcomes. And so we want to do the probability that our birthday is in July is going to be 31 out of 365. If we do 31 divided by 365, we're going to get 0.0849 approximately. We have to round on that. And then if we multiply that by 100, that's going to get us about 8.49%. Okay. So, what about that first problem that we were talking about? And we're going to talk about them in the next class. We're going to talk about the multiplication principle a little bit more. We kind of started it. I do want to go back to it really quickly. It says that suppose there are m possible outcomes for one process and n possible outcomes for a second process, then the total number of outcomes for the 2 processes is when you multiply them together. So specifically on this number of children, on the first child we had 2 possible outcomes. On the second child we have 2 possible outcomes. On the third child we have 2 possible outcomes. When you multiply those together, 2 times 2 times 2, you would get your 8, which is what we got right here, okay, for our possible outcomes. And that's what the multiplication principle says. On the days of the year, we didn't really have to do that because we know there's 365 days in a year. We weren't combining events. So we will talk about the multiplication principle a little bit more in the next class, but I want to go back to this. Let's go back to look at this. I'm curious as to what you think now. We look at this very first problem, this birthday problem. It says, suppose there are 25 students in your math class. What is the probability at least 2 students in the same class have the exact same birthday as you? It seems crazy, right? Because there's 365 days in a year. If I were sitting in this class, I would probably guess the 2 out of 365 if I didn't know, because I mean, we know that there's 365 days in a year, and those two people have to have a birthday, so that would be 2 out of 365. Is that right? 0.54%? What do you think? I want you to really think about, I want you to think about that question. I want you to even maybe research what you think. And I want you to come back with the next class, and I want us to really find the answer to this question. Would you draw a tree diagram on this? I mean, think about it. If you drew a tree diagram, you'd have 365 trees. That would be crazy, right? But then you'd have to draw 365 from each one of those. That would be a lot of work. Yeah, I just want you to, let's ponder over that. Let's think about that. Let's come back to that. So we're going to finish 7A in the next class. Feel free to ask me any questions that you need to ask me, or email me any questions that you have.